Hello, everyone, and thank you for the invitation and this kind introduction. So it's a pleasure to be here today. And in this talk, I'll be discussing recent advances and challenges in multimodal generative AI models. I will particularly focus on video language models and video generation models and how we can evaluate whether these models truly understand the physical world. So let us start with the question, what is generative AI? So at its core, generative AI refers to the models that can produce new content, such as text, such as images, audio, or video, by learning patterns from vast amounts of data. These models are capable of creating novel outputs that are often indistinguishable from human-made content. To contrast, discriminative models take an input like an image of a cat and assigns it a label. They just learn to distinguish between different classes by modeling decision boundaries. So in that regard, they don't generate new examples. So think of them as classifiers or detectors. And they have been the backbone of machine learning for decades, powering systems for image classification, object recognition, document classification, and sentiment analysis. However, they are inherently limited in expressive power compared to generative models. In generative models, we flip the direction of the task. So instead of assigning labels to inputs, the model learns to generate outputs that resemble the data it was trained on. So for example, we can prompt the model to generate a cat, and it will produce an image that looks like a plausible cat, even though that specific image may never have existed before. These models, of course, can process and generate not just images, so they can generate text, images, audio, and video, or a combination of these. They are fundamentally more powerful than the discriminative models in the sense that what they try to achieve is to learn the underlying distribution of the data. So if this is the original data distribution, with these generative models, we are trying to learn an approximate distribution of the original data distribution. And this process allows them, of course, to generate new samples from it. So, of course, these distributions could be distributions of images, distributions of text, distributions of audio, or even entire video clips that are consistent with what, of course, the model needs to see during training. So let's assume we are interested in image synthesis, image generation problem. So we want to generate images of cats through use of a generative model. Of course, this is far from a trivial task because it requires learning a model that can generate this high-dimensional, highly structured data. So in a natural image, pixels aren't independent from each other, but they follow some complex spatial and semantic patterns. For videos, this is even more challenging. So that said, of course, these models have advanced a lot in the recent years. So here is a result of OpenAI's Sora model. You've probably seen examples like this. You are providing a textual prompt, and then the model generates a realistic video. So in other words, the text is turned into coherent stories generated from scratch. Here is another example video generated this time by Google's recent VO3 model. So these are impressive outputs. But do they truly reflect real-world understanding? That's the central question. So how much do these models know about the physical world, about how objects interact, or about causal relationships? And I'll be talking about this today. Just like image and video generation models, Large language models, or LLMs, have grown dramatically throughout the years, both in terms of the scale and capability. So here, each box refers to a different large language model, and the sizes refers to the capabilities of those large language models. As these models become larger and more capable, of course, the question posed by Alan Turing in 1949 has once again become important. Can machines think? Turing reframed this question as the so-called imitation game, what we now call the Turing test. So the idea is simple. There is an observer and these participants, and there's a wall in between them. And if a machine can hold a conversation with the observer, indistinguishable from a human's, then perhaps it can be said to think. This question, once philosophical, is now increasingly practical, especially in the age of LLMs like ChatGPT, as these models can write, reason, and converse with remarkable fluency. There are some studies that suggest LLMs are already approaching or even surpassing human-level behavior in certain contexts. And that brings us to an important question. Is the Turing test still relevant today? Or do we need some new kinds of benchmarks, some new kinds of evaluations to truly assess the machine intelligence? In the rest of this talk, I'll walk through some of our own efforts to address this challenge by designing more targeted, more interpretable tests for language and video language models. But before we dive deeper, let me briefly explain how these large language models actually work. I suppose you all use ChatGPT, so you provide a text prompt, and then the model generates a response. But how does this happen? For instance, here you see a creative prompt asking the model to summarize the impact of generative AI on the humanities, while also including a reference to coffee, and it delivers a fluent, clever sentence that sounds remarkably human. Generative AI is transforming the social sciences and humanities as profoundly as the first sip of delicious coffee awakens the mind, including new questions, perspectives, and creativity with every invigorating cup. This kind of results is made possible and by training the model to predict the next most likely words, one word at a time, based on everything it has seen before. So that's the simple definition. In fact, long before the rise of large language models like ChatGPT, we have been using simpler language models in our daily lives, often without even realizing it. So autocomplete feature in search engines, predictive text on your phone. These are, again, the technologies that are powered by basic language models that predict the most likely next word or phrase based on what you have typed so far. They may not generate essays or codes just like the models like ChatGPT, but the underlying principle, next word prediction, is exactly the same. So let's take a closer look at what that means. In short, as I said, large language models are really just predicting the most likely next word over and over again. And here's how it works. Given a sentence like this one, let me stop. Okay. Behold a wild pie creature foraging in its native. The model processes this input and produces a probability distribution over possible next words. For instance, in this example, it might assign higher probabilities to words like land or forest or country, based on how it has seen the similar phrases used in its training data. And of course, then the whole process just considers one possible output, puts into the proper place, and then feeds this new sentence to the model. And then again, you get this new distribution. You perform as the sampling process, and it just goes on like that. In fact, the training of these models is based on exactly this task, next word or next token prediction task. Of course, it is applied at massive scale across vast amounts of text. Language modeling, of course, alone isn't enough. For these models to be truly useful, they need to understand what the user actually wants, the main intention behind the input. Before the rise of, especially this instruction-tuned LLMs, we typically had to train separate models for each task. For instance, one model for the translation, another model for the summarization, and so on. So here you see examples of this. So I used an automated machine translation system, so I don't know if there's a mistake. Sorry for that. And even this multitask models struggled because they weren't given clear instructions. To enable the flexibility of understanding the user intents and then performing the tasks, the desired tasks, of course, we need to rely on a process called instruction tuning. Here, the task instruction becomes a part of the input. So instead of just training separate models for translation, for summarization, and so on, we train just a single model to handle many tasks. By expressing the task clearly in natural language, as demonstrated over here, the model learns to follow the instructions directly. This makes it much easier to generalize to new tasks, even in zero-shot settings. With instruction tuning, models can be naturally and easily generalized to new or unseen tasks. Here's an example where the instruction is simply summarized in Finnish to make it easier to remember. The model takes that instruction and produces a coherent summary in Finnish, even though it wasn't specifically trained on that particular instruction prompt. So in the previous slide, I showed that there are some instructions for the translation and some instructions for the summarization, but summarization is carried out in English. And here, in a way, we are composing those two tasks into a novel task. But this flexibility suggested by the instruction tuning process makes these models so powerful. They can handle a wide range of tasks. And all through using these natural language instructions. With the advent of models like GPT-3, GPT-4, the names for ChatGPT, we've witnessed a major shift lately from purely text-based models to multimodal large language models, or MLMs in short. These models can now handle not just text, but also images, audio, and video, enabling a much richer and more flexible form of interaction. And most of those multimodal large language models follow a very simple and modular architecture. First, a pre-trained visual encoder processes the image and extracts some meaningful features. So this is again an AI model specialized for some vision tasks. Then a trainable adapter maps those features into a form that the pre-trained large language model can understand. And finally, the LLM generates responses integrating both the visual and the textual information. This modality allows us to plug powerful vision and language components all together without training everything from scratch. So you only need to perform training over this adapter module, and there are different strategies to do that. These models can take then not just text, but both text and images and input, allowing to perform a wide range of tasks from visual reasoning to rendered captioning to interactive dialogue involving visual content. Of course, one of the most widely known example is ChatGPT, where we can also use images like that. And in this example, GPT-4, this ChatGPT, can interpret the unusual visual scene. So the task is what is unusual about this image. It uploads this visual content, and ChatGPT correctly identifies what's odd. The unusual thing about this image is that a man is ironing clothes on an ironing board attached to the roof of a moving taxi. So it's like a clear demonstration of its ability to understand and reason about the visual content. However, this is a closed model in the sense that the architecture behind it, the details about the vision encoder, the adapter modules, and the language model are hidden to the users. We actually do not know any details about them. And of course, every IT company has its own large language model. Google has introduced Gemini, their family of highly capable multimodal models. And here's an impressive example. So the model is this time given a handwritten physics solution and asked to reason about the steps, determine if the solution is correct, and if it is not, explain the mistake and solve the problem. And if you look at the response over here, you can clearly see that Gemini identifies the conceptual error. So the student used the length of the slope L instead of the height H in the calculation of the potential energy. And then it explains the correct reasoning, showing the proper equations, giving the right answers, etc. So this example highlights how these models can not only interpret text and images together, but also performs structured reasoning over complex inputs involving diagrams and handwritten notes. In recent years, we've seen these models extended to handle video as an additional modality, allowing them to process and reason over both visual and temporal information. Video Llama is a great example of this shift. So it's trained to handle instruction-tuned audio-visual inputs, meaning that it can take a video, an audio stream, and a user query and respond accordingly. Here you can see examples of it summarizing the video content, describing what it hears, and even answering special questions like determining the direction of a moving ship. So this demonstrates how this video LLMs are becoming more interactive, grounded, and useful in real-world video understanding tasks. You can use these video language models to analyze, describe, or answer questions about videos in a flexible and intuitive way. So this example shows another model, Lava Video, describing a living room scene and getting in a dialogue with the user.
Hi, here's my living room, so please help me describe. Cool, thanks. Now I feel a little bit thirsty, so where I can get some drink? Thanks, let me go to the refrigerator to get some water.
So in that sense, as you see, the model not only identifies the objects and the arrangement, but infers some higher level semantics like the want of the space, the cluttered countertop, etc. So it demonstrates how multimodal LLMs are moving beyond object recognition into more holistic, context-aware video understanding. These models can describe visual content in fine detail as well. For example, this ShareGPT-4 video provides frame-level narration, identifying some subtle transitions from one keyframe to another, containing like a shift in hand position, changes in focus, or for instance, the progression of some cooking steps. So it shows how advanced these video language models can track fine-grained temporal events and highlight specific actions within a larger process, supporting applications like instruction following, video summarization, and content indexing. Erkut is another recently proposed video captioning model, which is specifically designed to generate fine-grained descriptions across multiple dimensions. Here again, an example. So in this case, it produces captions, not just about what is shown visually, but also about some additional notions, such as the background setup, the main objects involved. So you can see that it generates a short summary, a background-focused caption, and the caption about the main object. So it says that the main subjects are two smartphones, one on the left and one on the right, etc., etc. So this approach helps to capture contextual, spatial, and object-specific information. Google has also a project called Project Astra, which is again about building a universal AI assistant. And this assistant again will be built upon the similar kind of techniques based on this multimodal large language models. Again, this is a promotion video.
How should I wash this?
The tag shows to machine wash at 30 degrees Celsius. Avoid bleach and tumble drying. Iron on low and dry cleanable.
Then what setting should I use on this machine?
Based on the laundry instructions of 30 degrees Celsius, select the 30 setting under Easy Care on the dial.
Of course, everybody wants these kind of AI assistants. So far, I've provided an overview of the current landscape in generative AI. And in the remainder of my talk, I'll focus on two of our recent studies that benchmark generative video models. So the first work of ours I want to talk about, it's called Wilma, is about evaluating video language models through control tests that assess fine-grained grounding abilities, especially temporal understanding, spatial reasoning, and visual linguistic alignment. So we observed, as I said, a rapid evolution of large language models throughout the past few years. From early models like GPT-3 and T5, we've seen an explosion of such models from different institutions such as OpenAI, Google, Meta, Microsoft, and many others. So just like these LLMs were pre-trained on massive text corpora, video language models or video LLMs are pre-trained using, again, self-supervised learning on large-scale video and text pairs. So this often involves learning from instructional videos, narrated clips, or even subtitles. They are then evaluated on some downstream tasks, such as the ones that I showed you in the previous slides, like visual question answering, summarization, captioning, retrieval, typically in zero-shot or few-shot settings. These tasks test how well models can understand complex, time-dependent information from videos. Of course, the question is, do these models truly understand, or are just they picking up some patterns, like the dog in this cartoon? So we ask whether they generalize across tasks or rely on shortcuts, and whether they ground both reason and language in a meaningful manner. Wilma, our benchmark, follows a two-stage evaluation setup. In the first stage, that we call the proficiency test, we assess whether the model has basic recognition abilities needed for some complex tasks, such as, for instance, in this example, the object recognition. And this proficiency test is important because it is considered as one of the basic abilities that you expect from such a multimodal model. The second stage, that we call the main task, challenges the model with harder questions that require understanding temporal changes or causal effects in the provided video. And to ensure models aren't relying on shallow patterns, we use foils in our analysis. When we say foil, we mean the captions that are only slightly different from the correct ones, but are semantically wrong, such as in this case, someone folds the paper is the correct caption, and the foil is someone folds the laundry. And this, using these foils, forces the model to pay attention to meaning rather than picking up on surface level cues. And our benchmark includes 5 different tasks with unique phonic functions and proficiency tests. So the tasks are action counting, situation awareness, change of state, rare actions, and spatial relations. In the next few slides, I'll briefly walk through each of these tasks. In the action counting task, the model needs to determine how many times a specific action occurs in the video. For example, in the provided example, this refers to counting how many times someone lifts weights. So in that sense, the model must distinguish between subtly different captions, where only the variation may occur by the number of repetitions. And again, the proficiency involves, in this case, understanding the activities. So this does not just evaluates the recognition abilities, but fine-grained temporal tracking. In the situation awareness task, the model must interpret how visual cues aligned with the narrative. It is not enough to recognize objects or actions in isolation. The model needs to understand who is doing what, how they interact, and how those interactions relate to the given verbal context. This requires a deeper integrated understanding of the scenes. In the change of state task, the model must identify how an object's condition evolves over time by recognizing key sub-events. For example, in the provided example, it needs to determine whether a cup is full or empty at the end of a given video. Of course, this requires an understanding of both the starting state and the transformations that occur throughout the sequence. Rare action task evaluates whether models can detect atypical action-object pairings, such as spraying a door, in this example, instead of opening it. So it tests the model's ability to distinguish plausible actions from unlikely ones based on the context. Spatial relations task tests the model's understanding of spatial or spatiotemporal relationships. For instance, in this case, we let the model to distinguish between spilling water onto a plant versus spilling water from a plant. So this is the main task. Of course, as I said, the proficiency involves some basic recognition ability, and the model, we expect the model to recognize the objects well as well. So in this setting, of course, we need to be sure that the foils are of high quality. And in our experiments, we validate the quality first in an automatical manner, using mask language models for plausibility, natural language inference models for contradiction, and the board-based green scores for grammar check. And this helps to filter out some nonsensical or ambiguous candidates. Then we complement this automatic filtering process with some human validation. So we carried out an extensive user study on Amazon Mechanical Turk. So this is the screenshot of the first page of that user study. So we provide the workers an instruction. You will see a series of videos, each accompanied by two short texts. Your task is to judge which of these two texts accurately describes what can be seen in the videos. We can see the videos as many as time, and we provide some examples. And we let the users to select an option from the provided menu. And the foils, we kept the foils only if they if at least two of the three annotators agree that the foil is both plausible and clearly incorrect. Then we evaluate a broad range of models on our benchmark. A random baseline, the unimodal text-only models, image language models like CLIP and BLIP2, and a broad list of video language models. And in our analysis, of course, we have two options, a ground truth caption and a foil. So we measure the pairwise ranking accuracies. Does the model prefer the correct caption over the foil? And we did it for both the proficiency task and the main task. But as I stated, considering the proficiency is important because it checks the basic recognition abilities of the objects, whether they recognize the objects and the activities. And then we combine the results of them, whether they both succeed in the proficiency and the main task. So I don't go into the numbers, but there are two key takeaways here. First, video language models don't reliably outperform image language models. And this, of course, questions their ability to reason about temporal information. So if you look at the overall scores, you can easily see that the image-only models, CLIP and BLIP2, performs much better than most of the video language models. Second, the proficiency tests reveal that some models succeed by chance or by relying on shortcuts. So in that sense, they perform well on the main task, but perform poorly on the proficiency. And this highlights the importance of controlled benchmarks like ours. So for instance, if you focus on that, the model performs really nice on the main task, but the average accuracy for the proficiency is much lower, which you not expect for such a model. Okay, so that's LINMA, our benchmark for assessing the performance of video language models. The second work I'd like to highlight is PhysWithBench, a recent benchmark we designed to evaluate how well video generation models understand physical common sense. So it moves beyond static image evaluation and examines whether models can generate videos that reflect real-world physical principles like causality, material behavior, and object interaction. So video generation has improved dramatically in fidelity, as I demonstrated before. We have models like Sora and Veo that can produce longer clips, realistic motion, and consistent layouts. But this process in visual quality often masks a lack of physical understanding. So we need to move beyond what looks real and ask whether the model can simulate the world in a physically plausible way. So for instance, consider this prompt, and suppose a water bottle to pick up an egg yolk. So when we read that prompt, we can easily visualize the corresponding action. So let's see what these top performing models like Sora and Veo do on this prompt. So this is the result of Sora. So as you see, the result is visually and temporally impressive, producing some high quality output. However, despite its strengths, you can easily see some errors in physical dynamics, like some implausible object interactions, and it does not reflect the desired action stated in the provided text prompt. So there's still a gap in physical common sense. And this is the same issues appear in Veo 3 as well. For example, in this example, you can easily see that the water bottle deforms in an unrealistic way and doesn't interact properly with its surroundings. So this highlights that while visual quality is high, the underlying physical understanding of these models is still lacking. And our benchmark addresses, in that sense, a unique gap in the existing evaluation efforts. So there are some prior studies, prior benchmarks, but they mainly focus on some general plausibility or aesthetics. On the other hand, our benchmark with Bench centers on mostly tool-based tasks, requiring models to demonstrate fine-grained physical understanding of object behavior, causality, and interaction dynamics in a real-world setting. So in that sense, our benchmark is designed for evaluating the physical common sense in these video generation models. It does not contain very large number of prompts. We only have 383 prompts, but we are sure about their quality. So these prompts are adapted from the PICA benchmark dataset, which is a benchmark suggested for assessing the physical common sense abilities of the large language model. So it's like a question and answering type data set. So there's a question regarding a physical, a common sense, physical common sense, and we have these multiple choices. So in that sense, what makes our benchmark distinct is its structure. So we organize these prompts around 7 core dimensions of physical reasoning, from object properties to force and motion. So each dimension highlights a different aspect of the model's physical understanding. And in the next few slides, I'll briefly walk through each of these dimensions. The fundamental physics dimension then implies evaluates whether models grasp the basic rules that govern physical systems, such as energy, conservation, causality, equilibrium, and state transitions. So we are asking, does the model know that the objects doesn't just float midair, disappear suddenly? And with that, we can try to simulate cause and effect interactions in a physically plausible manner. So for instance, consider this prompt and place several sheets of white styrofoam into the bottom of a terracotta planter. So in this case, the model needs to understand how placing styrofoam into a planter affects the outcome. It's not just about objects, but reasoning through the physical setup and its implications. In the object properties and affordances dimension, we are interested in whether the models can reason about what objects are and what they can do. It's not just about recognizing, for instance, in this case, for this prompt, recognizing a cardboard tube or a dryer flint, but understanding their physical characters like softness, rigidity, and or containment ability. Can the model infer that lint can be compressed and stuffed into a tube? So this task requires models to connect appearance with function and understand how physical attributes translate into practical uses. So by the way, these videos are the results of the Sora model. So as you see, Sora fails to generate satisfactory results for these kind of prompts. The spatial reasoning dimension focuses on how well a model can interpret and generate correct spatial relationships between objects. So in the sense, you need to the model needs to understand geometry, orientation, occlusion, and how objects fit together in a scene. So for instance, in this example, the model is asked to show toothpaste being applied to the inside of the swimming goggles. It needs to reason about the containment and the positioning. But again, if you look at the results, instead of the inner lens, the toothpaste is smeared on the outer lens of the swimming goggles. Again, this is a failure. Understanding the order and pacing of actions is also crucial for realistic video generation. And this temporal dynamics dimension tests whether models grasp what should happen first, what comes next, and how to represent delays or waiting periods. It's all about modeling event sequences and causal relationships over time. Many everyday tasks follow a clear step-by-step process. So think of making a coffee, tying a shoelace, or for instance, in this case, separating an egg yolk from the white, like in this example. So this dimension evaluates whether the model can represent and generate coherent action sequences that move towards a clear goal. It's not just about recognizing individual actions, but also about understanding how they are organized to accomplish the provided task. Again, how do materials respond to external forces? An important question, and we also need to evaluate whether these models can handle with that. So in this example, for instance, can the model show the toothpaste being squeezed, cloth folding, or wax melting in realistic manner? This dimension focuses on material interactions and transformations. So we test whether the models can depict physical state changes like deformation, breaking, or flow. It's crucial for capturing realism and grounding scenes in the physical world. Finally, we assess how well models understand physical interactions involving motion, such as pushing, pulling, lifting, or collisions. Can they correctly depict effects of inertia, gravity, or friction? These prompts often involve tool use or some body mechanics under force. So, and we try to test whether the models generates dynamics aligned with the basic rules of physics. So as you see, we can just qualitatively examine these results to see their successes or failures of these models. But we also construct, we also need to perform a quantitative analysis. But before talking about that, let me briefly discuss how we construct our benchmark, how we obtain these prompts. And for that, we follow a 4-stage pipeline. We start with the correct answers from the PICA dataset. I mentioned it's like a physical common sense dataset for large language models. And we perform a filtering process over the existing samples using a large language model to identify the samples that involve secondary tool use and object affordances. And with that, we try to isolate examples that require deeper physical understanding. In the second stage, video prompt generation stage, we take these filtered solutions and convert them into concise, visually grounded prompts using, again, another LLM pass. These base prompts describe the scene in a way that's suitable for video generation. It captures the key actions, objects, and their physical setup. In the third stage, each base prompt undergoes an upsampling step. Here, we use another LLM pass to enrich the scene with fine-grained physical detail, like the way the objects deform, include additional attributes to the objects, etc., etc. And this helps to ensure that the prompt is much richer, reflecting not just what happens, but how it happens, preserving the logic and affordances of the original situation. Once we obtain these prompts, both the base and upsampling prompts are fed into a diverse set of state-of-the-art text-to-video generation models to obtain videos that probe tool-view interaction and these physical common sense properties. And here you see sample generations from 5 state-of-the-art open models, video generation models. So each example demonstrates the different dimension that we considered in our benchmark datasets. So despite impressive visual quality, I suppose we can easily pinpoint some of the failure cases. In these examples, the models fall short in capturing the physical dynamics of the scene. Either the objects behave unrealistically, or the interactions are incomplete or incorrect. And sometimes the key steps in the task are often missing or out of order. So again, these results highlight the central challenge in these recent models. So generating videos that are not just visually plausible, but also physically coherent and causally accurate is a really challenging task. As I said, once we obtain these videos, we examine them qualitatively, but we also perform a quantitative analysis. And to quantitatively assess the performance of these models, we again consider modular evaluation pipeline. It consists of 3 separate stages. In the first stage, we generate some yes/no questions directly from the upsampled video prompts that are being used as an input for the video generation models. So each question targets one of the 7 physical common sense dimensions that exist in our benchmark dataset, and is designed so that the correct answer is always yes. So these questions are fully answerable using just the prompt, so no external knowledge or video is needed. So our goal here is to create a structured, interpretable way to later evaluate whether the model's generated video matches with the intended physical scenario. In the second stage, we use the Aurora Cap model, the model that I demonstrated in the first part of my talk, this video captioning model, to generate 8 dense captions per video. So we produce 1 general purpose caption and 7 dimension-specific captions, each aligned with a different physical common sense category, like the spatial reasoning or the material interaction. And these generated captions, serve as an intermediate representation of the generated video that are then to be used while evaluating whether the video aligns with the original prompt and the physical expectations. In the final stage, we use a large language model to judge the correctness of the video. So since we use an LLM, it does not use a video. What we use is we feed the LLM the physics-granted yes/no questions from the first stage, and the captions generated from the stage and the intermediate representation of the generated video. And if the model answers yes to a question based on any one of the 8 captions, we count it as correct. And then we compute the final accuracy as the proportion of correct answered questions across all evaluated videos. Here is an example of how we create these interpretable evaluation questions. So this is a prompt describing a multi-step physical interaction involving toothpicks and a leftover cake. So it includes detailed references to object properties such as a wooden toothpick. Or some physical manipulation processes are pushed with steady pressure. So from this single prompt, we can derive targeted yes/no questions, as I said, as the first step of our evaluation setup. And here is the set of yes/no questions derived from the previous prompt. And here is the video generated by the Huan-Yuan model. And you see the success of the provided output. So despite some partial success, we observe that it fails in capturing, for instance, the firmness of the grip. So these questions help to diagnose precisely where this model falls short, whether in physical realism, causality, or the goal-driven coherence. And here you see the overall table summarizing the accuracy scores for different video generation models across our 7 physical common sense dimensions. Again, I do not want to bother you with the numbers, but we have some important findings. Despite the progress, even the best performing models like Cosmos 14 billion still struggle with tasks that require physical reasoning, particularly those involving temporal dynamics and object relationships. So for instance, if you look at the accuracies of these models for the temporal dynamics dimensions, really low. So this shows that despite recent progress, current models fall short when it comes to understanding how the world works. Second, we need, again, the scores are very low. So this demonstrates that we need better architectural designs and training models. So more scale alone isn't enough. So we need models that are explicitly trained to reason about physics, causality, and procedural sequences, not just visual pattern replications, if we want to use these models as the world models. So to wrap up, let me reflect on where we are today. So I stated that generative AI today can produce highly realistic text, images, and video. LLMs and multimodal versions, MLLMs, are reshaping how we access and reason about information across modalities. But as our results, our findings demonstrate, despite these impressive visuals and the abilities, the models still struggle with some physical reasoning and physical plausibility. So many rely on some shortcuts and fail at tasks involving especially temporal understanding or common sense interactions. Closing this gap will require better models, but just as importantly, better benchmarks and evaluation strategies like the ones we proposed. So thank you for your attention. I'm happy to take your questions.
Thank you, Erkut. That was fascinating. We do have time for a few questions, comments. Do we have any? First of all, well, I have a couple. So you mentioned in your talk how the video models were not faring better than the image-based models in your tests. So do you think is that something inherent in the video models, or is it simply that there is just kind of work to do to improve the video models?
Mm-hmm. So it's a good question. So it depends on several different factors. So most of the time, these models were trained on vast amount of data, and especially in our cases, so the results that I showed you was a year ago. So in that sense, the models are not up to date, and we see that every day, maybe not weeks, we face up with some new models, and these models considers much cleaner data, because when we are training these models, the provided video should align with the provided narration or the caption or the subtitle. And sometimes if there's a misalignment, of course, this affects the performance of those models. Secondly, again, if I remind you the basic structure, so you have a vision encoder, you have an adapter module, and you connect the visual encoder with the LLM. And for these models, how you perform this connection do matter, because in the if you are considering images, everything is very simple. So you have just a static image, you can easily take the semantics. But for the videos, there's this temporal dimension as well, and these encoders should provide you the necessary semantics about the activities being happening in these cases. So most probably, we also need to have some stronger encoders, some stronger feature extraction mechanisms for the video contents.
Yeah, good, thank you. Somebody?
I would have a question. Thank you for your nice presentation. It was really impressive. I'm just wondering for the future, probably. There's been discussions about the media and news where there is a lot of fake information and produced and these. And now these examples that you were showing are very nice, because when people's literacy on these aspects is not the best yet, so they don't maybe know when the information is true and maybe it's when it's false. So as here were examples how you can produce still images or videos from the text that might also then in the future support the literacy of people. And if we think about the intercultural communication or how people in general can understand each other. I think these kind of tools can be also used for that. We have a lot of conflicts in this world, so these kind of tools could help us in the future also easier to find the information that is truthful and what is false. So thank you for your presentation.
Thank you.
Thank you. You want to comment on that? Or?
Yeah. So I agree. So there's this upsurge in these models. Of course, when these models become more and more capable, it becomes really hard to distinguish the real from the fake. So this deepfake had become a problem even nowadays. But for instance, some big IT companies embed some watermarks, which demonstrates that these are not real videos, but they are synthetically generated. But there are these open models as well. And of course, we could not be offsure that whether a video will be real or not. Currently, as I demonstrated, they have some failure cases. But if you think about that, the whole interest over these models started just a few years ago. We actually don't know what happens in the upcoming years.
Good. Kristen?
I don't know if you can hear me, guys.
Yeah, maybe better.
Yeah.
We have the microphone.
Close to the microphone. So in order for these to be useful for research purposes, one would want to input rather long prompts or use some RAG method. So how is that tackled currently? So how long prompt can they take, and is that something that is being researched?
It's again a really good question. I did not want to go to details of these models, but as you pointed out, if we want to make these models more practical, there should be no limit on the provided size of the text prompts. And in the recent years, this is again an open research problem. The context sizes of these models have increased a lot. So we have these long context models. For instance, the examples that I showed you here just considers videos of 10 seconds or 20 seconds. But especially this year, I came up with some video large language models, for instance, that can process hours of video as well. So I suppose in the near future, these models can process larger inputs, not just text, but in the visual part as well.
Okay, so maybe if I just to try to kind of reply also something I was about to ask, but I just want to make sure. So when talking about using these models to summarize or describe video content, this has been mainly done for relatively short video clips. So kind of how do you see where is the limit for kind of can we use that for kind of 2 hour long?
So everything depends on the architecture. So again, these models generally depends on the transformers as the main architecture, and transformers has a fixed window size for the provided text prompts. So in that regards, the current trend is, for instance, if you have considered a video, maybe not all the frames are not that important. So we can, in a way, compress the visual content of a video of an hour into much smaller features, smaller size features. So instead of extracting features for every frame, we can perform compression, or we can even perform some selection operations over the video tokens extracted by the given cases. And there is like a huge interest nowadays, because if we want these models more practical, of course, there should be no limits over the size of inputs, not for the text, not for the visual parts as well.
Yeah, thank you. So do we have any more questions? If not, then thank you, Erkut. That was really interesting, and I'm looking forward to welcoming you in Jyväskylä in a couple of months.
Yeah, me too as well. So thank you again.
Thank you. Have a nice weekend. Bye-bye.
Yeah, you too.
And now, Krista, do you want to give your opening words now,